Hello everyone, welcome back to my channel. I am Vihan, a perfect AB Precal 5 kid. I took the test when I was in 9th grade and I got a perfect 5. I'm currently in 11th grade and I've started this video series since last year. Now I know that College Board does not give out the official multiple choice practice of AP Precal, and I was one of the first kids to have sat for this test the first time it was introduced. So I know exactly what questions they asked me on my multiple choice. So although I have made these questions on my own, I can guarantee you that these are very much relevant to your test. I have a total of 35 questions with me, and I'll be having them in 5 videos of 7 questions each. So if you like the videos and if you feel that you want to look at all 35 of them, make sure that you watch all 5 videos. Apart from that, the entire 35 question PDF along with the answer key is linked in the description below. If you do choose to directly go to the PDF instead of looking at the video, I would really appreciate if you leave a like or a comment. It would really help me since I'm applying to college as well. Yeah, so let's begin. Here is question 8, have a try. Alright, question 8, we have a function, we have a rational function, and we have to figure out vertical asymptotes and holes. So whenever you look at vertical asymptotes and holes or even horizontal asymptotes, I want you to factor the polynomial. So I want you to factor the function. So x square minus x minus 6 is x minus 3 into x plus 2, and the denominator is just difference of squares, which is x minus 3 into x plus 3. Now this isn't exactly a very important question, but it is a very important concept that will be tested on your multiple choice. You need to know the distinction between a vertical asymptote and a hole. So if for instance I call my numerator n and denominator d, then I have a hole when both the numerator is equal to 0 and the denominator is equal to 0. That is when we have a hole. We have a vertical asymptote when the numerator is not equal to 0 but the denominator is equal to 0. This is a distinction you must be clear about. So if I look at the function at x equal to 3, both my numerator and denominator go to 0. So I have a hole at x equal to 3. If I look at x equal to minus 3, only my denominator goes to 0, my numerator does not. So I'll have a vertical asymptote at x equal to minus 3. And that is all you need to know. If I glance at my choices, I have a vertical asymptote, no, not this one, a hole at x equal to 3 and a vertical asymptote at x equal to minus 3, yes, this should be it. A hole at minus 3, no, not this one, holes at both, no. So understand that if you have the concept clear, this becomes very intuitively easy. So yeah, 8 is B. Next up is question 9, have a try. As I previously mentioned, whenever you're dealing with holes, vertical asymptotes, you must factor the function. So over here, if we factor the numerator, I get x plus 2 into 2x minus 1. And if I factor the denominator, I get 2x plus 1 into 2x minus 1. And rightly so, we have a hole at x equal to 1 by 2, as both the numerator and the denominator go to 0 when we plug it in right here. So in order to find the y-coordinate of the hole, you simply remove the common factor which arises the hole, and then you plug back in the value of x. So we have into the remainder of the function, yeah. So we have 1 over 2 plus 2 upon 2 into 1 over 2 plus 1. This should be 5 over 2 upon this goes, and we have 2, which is 5 over 4, and hence your answer is option C. Alright, question 10. Which of the following rational functions has a horizontal asymptote at y equal to 3 and no vertical asymptotes? Again, pause the video, have a try. Now we have two conditions here. One is horizontal asymptote at y equal to 3, another is no vertical asymptotes. Yeah, you can approach it either ways. Maybe you can look for no vertical asymptotes and then go with horizontal asymptote, or the other way around. I'll go as the question directs me to. So I have a video where I go over all the rules of horizontal asymptotes, so I'll be going through them relatively quickly here. If I look at option A, my degree of denominator is greater than the degree of the numerator, which is 1. So I have a horizontal asymptote at x equal to 0 here. This is not, sorry, y equal to 0, and this is not what we want, so option A isn't it. If you look at option B, yes, I have the degrees the same, and when the degree is the same, the horizontal asymptote is just the ratio of the coefficients, which is 3 over 1, which is 3. Yes, this is something we're looking for. Option C, degree is same, but the ratio is 1 over 1, which is not equal to 3, not something we're looking for. Option D, again the degree is same, and we have 9 over 3, which is equal to 3. So option B and D survive the horizontal asymptote test. Now we need to have no vertical asymptotes. We have no vertical asymptotes when the denominator can never be equal to 0. Now if you look at the denominator of option B, it is x square plus 5, yeah, and x square plus 5 can never be equal to 0. Yeah, it's always greater than 0. So this is a strong contender. And if you look at this one, which is 3x cubed plus x, yeah, if you factor the x out, you have x into 3x square plus 1, and surely 3x square plus 1 can not be equal to 0, but then x can be 0 as well. So we have a vertical asymptote, so our answer is option B. Alright, question number 11, have a shot. This is an important one. Now in this question, a common mistake I've seen everyone do, including me myself, was that we multiply x minus 3 to the other end. So we have 2x is less than x minus 3, and then you subtract x from both sides to get x is less than equal to minus 3, and then you wrongly get this interval minus infinity to minus 3, which hopefully isn't a multiple choice option here. If it were minus 3 over here, then yes, many of you would have chosen A, but in doing so we actually lose an entire solution interval. So I'll show you the correct way. If we have 2x by x minus 3 is less than equal to 1, yes, the approach of making one side less than or greater than 0 is correct, but instead of multiplying x minus 3 to the other side, we actually subtract 1 from both sides. So 2x by x minus 3 minus 1 is less than equal to 0, which gives me 2x minus x plus 3 over x minus 3 is less than equal to 0. This should give me x plus 3 over x minus 3 is less than equal to 0. And then, as I explained in one of my previous videos about how you have the number line approach to solving these questions, you have a number line. I have two critical points, one is minus 3, another is 3. Here I have minus infinity, and here I have positive infinity, and then I pick my 3 intervals like this, and I have a test value. So if I have x is equal to minus 4, I'll have a negative upon a negative, which is a positive. So this is a positive interval. For the middle one, I pick x equal to 0, which is a positive over a negative, which gives me a negative. So this is negative. And if for the last interval, I pick x equal to 4, this gives me a positive over a positive, which is positive. So this interval is positive. Now what are we looking for? We're looking for negative solutions. So ideally minus 3 to 3 is the only solution that we have. Now you have minus 3 and 3 both here, but notice the square bracket. The square bracket means minus 3 is included, and the round bracket means minus 3 is not included. Now if we put minus 3, we actually have this thing going to 0, yeah, which is equal to 0, and our sign permits equality to 0. So our answer will be option B and not option C. I hope that was clear. Here is question number 12. Have a try. This one is relatively easy, so I won't be spending a lot of time. We need to figure out the value of f of g of 3 plus g of f of 2. Now in function composition, you must be very clear with what's the input of what and what's the output of what. So the input of f is g of 3, yeah. What is g of 3? If you look at the table, this is g and g of 3, so 1. So f of g of 3 is f of 1, and f of 2 here, f of 2 is simply 1, so we have g of 1. Now what is f of 1? f of 1 is 4, so this is 4, and g of 1 is 2, which is 2, so 4 plus 2, that should be equal to 6, and that's your answer. Alright, question number 13, again this is relatively easy, have a shot. So we have two functions f and we have a function g, and we have an unknown k right here, and it says f of g of x is x for all values of x. What is the value of k? So simply, without giving it a lot of thought, you just have f of g of x, which is 3 into, now instead of putting x, you put in g of x, which is x plus k over 3 minus 4, this is equal to x. Yeah, so this is x plus k minus 4 is equal to x. You subtract x from both sides and you're left with k equal to 4, so the value of k is 4. Easy. So question 14, again an important one. Like most of the questions that I have here are very much relevant to the test, and some of them which I emphasize strongly will definitely come, so you must be able to solve them, and question 14 is one of them. So function is defined for all values of x not equal to 1. Which of the following is f inverse of x? Now there are a few steps to finding inverses which you must know. First of all, we write the original function y is equal to 2x plus 3 over x minus 1. The first step to solving an inverse is to exchange the x with the y and the y with the x. So we should have x is equal to 2y plus 3 over y minus 1. Yeah, and then your only purpose is to isolate y. So I cross multiply, I get xy minus x is equal to 2y plus 3. Yeah, and then I add x and subtract minus 2y, so I have xy minus 2y is equal to 3 plus x. Yeah, and then I take y common, so we have y into x minus 2 is equal to 3 plus x. I'll write it down here, y into x minus 2 is equal to 3 plus x. Yeah, and then I send x minus 2 to the other side, so 3 plus x over x minus 2. That should be our inverse. Checking my answer choices, yes, these are the ones that seem to be correct, but then we have an additional thing which is undefined at x equal to and undefined at x equal to 1. Well, the original function is undefined at x equal to 1, but then our inverse is not related to what our original function was not defined at. Our inverse is defined at x equal to 1 and is not defined at x equal to 2, so option A is the correct one.